In this lesson, we're going to be exploring 3 inverse trigonometric functions. So far, we've studied 6 trigonometric functions: y equals sine x, y equals cosine x, tangent, cotangent, secant, and cosecant. But in this lesson, we're only going to study 3 of those 6 inverse trigonometric functions. To help us get started, let's revisit the 3 trig functions that we've studied in the past. So here we have y equals sine of x. Here we have a graph of y equals cosine of x. And here at the bottom we have y equals tangent of x. All right, to begin our study of the inverse trig functions for sine, cosine, and tangent, we want to revisit some of the points that we knew were on these other regular trig functions. So let's just kind of name some of the key points on y equals sine x. So here we have 0, 0. Okay, notice that my scaling here is not in terms of pi, it's just in terms of numbers. But we know what this graph looks like. We knew right here at this point, this was pi over 2, comma 1. So we can kind of see that pi over 2 is a little more than 1.5, so that makes sense. Here another key point was pi, comma 0. Here we had 3 pi over 2, comma negative 1. If you change 3 pi over 2 to a decimal, it'd be about 4.71. So we can kind of see that the x-coordinate here falls closer to 5 than it does to 4. And finally, we had 2 pi, comma 0. All right, to study the inverse sine function, you might recall from your previous studies that the word inverse means to switch the x and y coordinates. So let's take these 5 key points and interchange their x and y coordinates and plot those. So 0, 0 switched would just be 0, 0. When I switch pi over 2 and 1, my new point is 1, comma 1.5 approximately. So if I plotted 1 here and went up to about 1.5, my new point would be about right here. All right, let's go and switch the pi, comma 0 to 0 pi. So how do I plot that? We'll go back to 0 and then go up to pi, which is about right here. So starting to connect these points, I would start here at 0, 0. I would round my way up to 1, comma pi over 2. And I'd come back and collect this point right here. So let's go and plot the last 2 key points after we interchange them. So this point would be negative 1, 3 pi over 2. So how do I plot that point? Well, I go over to negative 1 and I go up to about 4.7. So that'd be about right here. So continuing to connect, I would be continuing up this way. Now right here, let's switch 2 pi and 0 and plot the point 0, 2 pi, which would probably put me about right here, back on the y-axis. And I could continue this pattern, and all I'm going to be doing is just kind of winding my way around the y-axis. Likewise, if I wanted to take these key points back here on this part of the sine graph and interchange their x and y coordinates, well, I'm going to have a graph that comes down like so, and then back to the y-axis. It's going to look something like this. So when we look at this inverse sine graph, okay, we can kind of see that it's just gonna kind of oscillate around the y-axis. Well, this inverse graph right here does not pass the vertical line test, so this inverse graph is not a function, but we want it to be a function. So what we do is we choose a part of this graph to be a function that would pass the vertical line test. And it's common practice for us to choose this section of the graph from this point to about this point right here. So if we just chose that little section right there, that little piece, we can see that this part of the inverse sine graph does pass the vertical line test. So this is now going to become our inverse sine function. So we're going to be interested in the domain and the range of this inverse sine function. So let's come to our other worksheet right here and record what we know. So when we talk about inverse sine, we can also call it arc sine. So the word arc and inverse mean the same idea. The alternate notation that we could use is y equals inverse sine with that little -1 indication here of x. So we could either say y equals inverse sine x or y equals arc sine x, and we're talking about the same graph. All right, let's go ahead and see if we can take and transfer this piece of the inverse sine graph, which is now inverse sine function, over here to this grid. I can see that the domain of this little highlighted piece goes from x equals -1 to x equals +1. So the domain of arc sine is going to be to include -1 and go up to +1 along the x's. Okay, and then our range is going to be from this low y up to this high y. All right, well, this low y down here is going to be -pi/2. So I'll scale it maybe something like this, up to +pi/2. Because remember, we switched this ordered pair, so now the y is pi/2. So we start down here in the bottom left, and notice the way we curve up to the origin. We kind of curve the graph this way. And the final point that's on arc sine is going to be up over here at 1pi/2, and notice the way we kind of curve back up to that point. So the range is going to be -pi/2 to +pi/2, and we include those because we do have endpoints. So when we talk about the inverse sine graph, which is a function, we're talking about just this little section right here, having the domain -1 to 1 and range -pi/2 to +pi/2. All right, let's explore the arc cosine graph. So back to here, maybe it'd be a good idea for us to name some key points on the regular cosine graph. So this is the point 0, 1. This point right here, the key point is pi/2, a little more than half, comma 0. This minimum was pi -1. This point right here was 3pi/2, 0. And then we were back up here to 2pi, comma 1. All right, let's see what happens when we interchange these ordered pairs and produce a graph. Well, 0, 1 becomes 1, 0. How do I plot that? Right here. That's where I'm going to start. My next point that I'm going to interchange is pi/2, 0. So I'm going to plot 0 right here up to pi/2. So what I'm going to do is I'm going to bend back this way. Next point, I'm going to interchange the coordinates right here. So I'm going to plot -1, +pi. So -1, +pi would be up here. So I'm going to have to continue my inverse graph for cosine this way. Let's interchange this ordered pair. We're going to plot 0, 3pi/2, which is about 4.7. So the graph bends back this way. And then finally, let's plot +1, 2pi, probably up here. Now we can continue, and this graph's just going to continue the same pattern above and below. All right, well, we can real quickly see that this inverse cosine graph is not a function. So what part of this inverse cosine graph do we choose and select so that that selection passes the vertical line test? Well, it's just common practice to choose this section right here. All right, so let's take a look at recording that onto our other sheet of paper. Okay, analyzing this section of the inverse cosine graph, I can see that the domain goes from -1 to +1, but I see the range goes from y equals 0 up to y equals pi. This is about pi if you were to extend it over to the y-axis. So let's go ahead and repeat this part of the graph over here. So again, we can call the inverse cosine graph y equals inverse cosine, using that little -1 notation. Or sometimes we just write y equals arc cosine. Those mean the same thing. So domain -1 to +1. But the y's go from y equals 0 up here to y equals pi. So let's think about where the graph starts. It's going to start right here at 1, 0. And about pi over 2, here it's going to cut through the y-axis, thinking about the way it bends, and then it bends back this way. So the range goes from y equals 0 all the way up to pi. And we have endpoints, so we use the brackets. Okay, just real quick too, before we move to developing the last inverse trig graph, let's remind ourselves about symmetry. Okay, inverse functions have the property that they're not only do you just switch the x and the y, but you also have symmetry along the line y equals x. So if I were to think about what y equals x looks like, I could plot something like this. I'm just going to dash it in. So this is y equals x. And I could extend back this way. Okay, symmetry means we've created a mirror image. So is y equals sine x a mirror image to y equals arc sine x? Yes, it is. Because if I were to fold along the line y equals x, I would see that these two graphs are mirror images. Same thing down here with y equals cosine x. Let's sketch in y equals x. Notice that if you were to fold along the line y equals x, that this part of the graph would lay on, or this graph would lay on this graph right here. So we've created mirror images. All right, same thing down here with y equals tangent x. So maybe without using points, ordered pairs, to switch the x and y coordinates, we can kind of visually think about what the inverse tangent graph would look like. Well, if we do remember also that for tangent, we have a vertical asymptote at pi over 2, and we have another vertical asymptote for this part of the tangent graph at y equals -pi over 2. Well, these vertical tangent lines, these vertical asymptotes become horizontal asymptotes when we reflect the graph across y equals x. So let's sketch in y equals pi over 2. So if I went up to pi over 2, which is about right here at 1.57, if I were to sketch in a horizontal asymptote instead of a vertical, it would look like this. Let's sketch in y equals -pi over 2, which would be about down here, as a horizontal asymptote. So our inverse tangent graph is also going to have symmetry with regard to y equals x. Remember, this is y equals x. Okay, so what would that graph look like if we were to reflect? Well, that graph would look something like this. It's kind of hard for me to draw, but I think it's going to kind of go up like this and follow out that horizontal asymptote. So if I think about a reflection across y equals x as best I could, looks like these might be mirror images. And then I'm going to come back down this way. So what happens if you were to reflect more than just this part of the tangent graph is that you would have a bunch of inverse tangent graphs that are stacked on top of each other. So I'd have another one right here and another one down below in this next section of horizontal asymptotes. But just think about it. If you were to stack a bunch of these similar graphs on top of each other, that would not pass the vertical line test. So we just choose this one part of the tangent graph to reflect, because now I will pass the vertical line test. so that now I have an inverse tangent graph. All right, so let's take and transfer this to our other page. Y equals arctan. Also, y equals arctan with the -1 symbol. All right, I have horizontal asymptotes at pi/2 and -pi/2. So let's sketch those in. Okay, we have a point at the origin, and we're going to follow this asymptote out to infinity, so I'm going to go ahead and bend the graph in this direction. And then I'm going to follow the y equals -pi/2 asymptote out to -infinity, so we draw the graph in this direction. So what's the domain? Well, the domain is all real numbers. Now the range is going to go from -pi/2 up to +pi/2, but we don't want to include those because those are horizontal asymptotes. So we use parentheses instead of brackets. Okay. All right. And I want to make a connection to the relationship between the domain and range of these 3 inverse graphs with the 3 regular graphs. So remember on sine x that the domain was all real numbers, and the range for the regular sine graph went from -1 up to +1. Well, remember, we're talking about inverse functions now, and so we switch the ordered pairs. We switch x and y, which means we can switch all the x's and all the y's. So on inverse sine, the domain becomes the range. So this domain, okay, could be the range right here, but if we let it be all real numbers, then we wouldn't have a function. That's why we had to restrict this all real numbers to just going from -pi/2 to +pi/2. However, these y values, the range on sine, do become the x values, or the domain, on inverse sine. Same thing with cosine. The regular cosine graph has a domain of all real numbers, but we don't want to take all real numbers on the inverse cosine, because if we did, we wouldn't have a function. So we restrict the domain, those x values, to just be some y values here. Remember, the range on cosine was -1 to 1, so those become the x's on the arc cosine. Okay, let's look at tangent. Tangents, we'll look at this one part of the tangent graph. Its domain on that one part was just -pi/2 to +pi/2. And its range for tangent was all real numbers. So let's switch the d and the r, or the x's and the y's, and that becomes the domain and range on the arc tangent. So switching x and y's is part of the whole inverse idea. Okay. Sometimes, depending upon what we're doing, it's helpful to think about the inverse graphs for sine, cosine, and tangent. Sometimes it's helpful to kind of think about where these inverse functions land, their range values anyway, on the unit circle. So this space right here is provided for us to look at a different representation of the range values on the unit circle. So let's draw 3 unit circles here, one for each of the arc graphs. So if we're dealing with arc sine, what I want to focus on are the angle measures -pi/2 to +pi/2. And where do those angle measures fall on a unit circle? Well, we definitely know that -pi/2 is down here, and I'm going to put a closed circle to represent inclusion. So if I go from -pi/2, the smallest range value, to +pi/2, that means I'm going to travel along the unit circle in this manner. and up here is the angle positive pi over 2. So think about that part of the unit circle that we just kind of darkened, and I'll highlight that. So whenever we're dealing with a question that asks us to find an arc value for sine, our answer can only be an angle that falls between negative pi over 2 and positive pi over 2. So let's talk about coterminal real quick. We know that this angle measured down here, if we went around in this direction, could also be called 3 pi over 2, but 3 pi over 2 does not fit in between these two y values. So we have to quickly rename 3 pi over 2 to its coterminal name, negative pi over 2, to fit within the range of arc sine. All right, let's take a look at the range values, the answer values for arc cosine. Well, if I have an angle measure that's 0 radians and I go to pi radians, I'm starting at 0 and I'm going all the way over to pi. Those are the only answers I can have if I'm asked a question about arc cosine. So if I see the word arc, or I see the -1 notation, and I'm asked for an answer, the only answers I can give are values between 0 and pi. And then finally, let's look at the range values for arc tangent. Well, negative pi over 2 to positive pi over 2. However, those endpoints are not included. Those y values are not included. So we want to indicate that with an open circle, but this is very similar to arc sine in that we're only looking over here on this part of the unit circle, quadrants 1 and 4. All right, we're going to be doing some work with these three inverse trig functions in the next video.